Welcome to this standing room only edition of the Pinkel Lecture Series. This is our 20th annual Pinkel Lecture. I'm David Brainerd. I'll be introducing the lecture series before I hand the mic over to Michael Kearns, who will introduce our speaker. The full name of the lecture series is the Benjamin and Anne A. Pinkel Endowed Lecture, and the fund was established through a generous gift from their daughter, Sheila Pinkel, on behalf of the estate of her parents, and serves as a memorial to the lives of her parents and a tribute to them. Benjamin Pinkel received his Bachelor of Science in Engineering here at Penn in 1930, and he was very interested in the philosophy of the mind and the action of the mind, and indeed he wrote a little monograph on the subject. I have a copy here, which our speaker will receive after the lecture, called Consciousness, Matter, and Energy. And the lecture series is focused on in the Endowed Fund, a re-examination of the mind-body problem in light of new scientific information. So over the years, we sometimes hear from philosophers of science about the mind-body problem, and sometimes we hear about scientific advances in the study of both animal, human, and artificial intelligence, and today's lecture will continue in that tradition. So with that, I will hand the mic over to Michael Kearns, who will introduce today's speaker.
Thank you, and welcome everyone. Thanks for coming. It's my pleasure to introduce this year's Pinkel Lecturer, Professor Les Valiant from Harvard University. Les, as I think many people in this tremendous crowd know, has made many, many fundamental and lasting contributions to many topics in computer science. And more than that, many of those subfields he in fact initiated or created entirely himself. This includes important contributions to computational complexity, to circuit complexity, to the theory of parallel computation, to computational learning theory, and algorithmic theories of neuroscience and evolution. He was really one of the first theoretical computer scientists to apply what is now colloquially called the computational lens to problems outside of computing, to the natural sciences and other areas as well. He is the recipient of virtually all of computer science's highest awards, including the 2010 Turing Award. The citation for the 2010 Turing Award was notable in its breadth of his contributions. Normally, the Turing Award is awarded for relatively specific contributions, and Les's citation is an outlier in that regard. On a personal note, I can also say that he is a wonderful and warm mentor and advisor who gave my own research career a start. So please join me in welcoming Les.
Thank you, Michael, for the more than generous introduction, and thank you for inviting me to this distinguished lecture series with a distinguished history. I'm particularly pleased to be able to talk in this series about cognitive science, since that has been a primary motivation of my work, as I'll explain. So the topic today is about machine learning and what directions it needs to be amplified to make it better. And by better, I do mean as explanation of cognition, mainly, and also as a test for whether you've got a good theory of cognition. So AI is like a test. And so these topics, I think many of you in the audience have thought about and have addressed, possibly in different directions. So there are very many angles to it. So I started in this area with a very kind of purist viewpoint, and that is that basically a question of semantics. So we've got a cognitive entity, namely you, and you operate in the world. And so while we could discuss what algorithms your brain uses, we could discuss at a high level what functions these algorithms perform, but an even more kind of fundamental question is, how do the bits of information in your brain correspond to the outside reality? And so this seems to be the most basic kind of question, and it seems that that's where we have to start. And the idea which drove me was that cognition is a very predictable phenomenon, amazing phenomenon, a bit like gravity or anything else. It must have some simple scientific explanation, And so questions like this should have a simple scientific explanation. So as a slogan, you could say that cognition cannot be a kludge of all kinds of artificial random bits and pieces. There has to be some simple explanation. So, so this is basically the setting I have. And so maybe as a guiding quote, which I've used for a long time, by Aristotle, who said that all belief comes from syllogism or induction. So if you believe in something, on what basis do you believe in it? So he said either through reasoning, so syllogism is like reasoning, or induction, which is something to do with generalization. So these two topics have obviously a long history since. So syllogism has become mathematical logic, reasoning, and whereas induction was regarded as a big philosophical mystery for many centuries, I think it's the one which machine learning theory kind of adopted and gave a scientific explanation for. Okay, so induction, in fact, seemed to dry up as a philosophical question many decades ago, but now, really, especially with the practical use of machine learning, I don't think people would even raise it. So the idea that generalization is some big inexplicable mystery wouldn't occur to someone who is exposed to all the hype about machine learning, which machines do generalization for us all the time. It can't be that mysterious. So what I'm really looking at is the basic semantics, and what the first thing I want to draw attention to is that logic and machine learning have very different formulations. So logic is this very kind of deterministic thing, and machine learning is a rather statistical thing. And the question is, if we have a theory of cognition, it can't be based on both. You have to make some choice. I mean, it can't be that when we think about something, we change our representation as to when we think about something else. And as far as semantics, so logic is a splendid field. It's done a lot to explain mathematics, but as far as applying formal logic to cognition, it's kind of not so successful. And I think the reason for it, you can just realize immediately if you think about the semantics. So the semantics of mathematical logic, so-called task semantics, is something pretty mathematical. But what it doesn't do, it doesn't really relate your belief to the world. So, for example, if you believe that all men are mortal, the semantics of logic doesn't tell you what this means. Have you verified this empirically? Is this true on every planet? So the semantics of traditional semantics of logic just doesn't answer this question, and that may be already an explanation of why formal logic is not a good basis for doing cognition. Okay, so I think so in our time, I think a good aim is to find a semantics which you can apply to both the processes of generalization and also of reasoning. So this is what I'm describing, and the technological aim would be to demonstrate that you've succeeded by solving a significant AI problem. And a significant AI problem is to have a system which can reason about common sense knowledge. So I'll say more about that later on. Okay, but I think I should mention that, as I said, this quotation I've used for a long time, but I've realized that, in fact, I'm changing its use. So in the early days, when everyone believed logic was a well-founded mathematical discipline and induction was some flaky thing, I used to put this up to say that, look, Aristotle was a reasonable guy, and even he thought induction was important, okay? So now I've flipped. I'm saying, look, Aristotle was a reasonable guy, and even if you think that machine learning solves all the problems, there's still reasoning. Okay, so let's not forget about that. Okay, so so that's the general message. Okay, so I'll ask you a question now. Did Aristotle have a laptop? And this is you probably know the answer, but the question is, how did you get this? And the point I'd like to make is that it's unlikely that you reached the conclusion by being trained on lots of sentences about Aristotle and his property, or who had laptops or pictures of these things. Okay, so you weren't trained like a machine learning algorithm on lots of examples of sentences like this. So you must have used some other process. And so presumably that's the process where we need some sort of reasoning. Okay, so to make this a bit more scientific, so the question is, can we make this into an AI problem which is quantitatively evaluatable? Okay, rather than looking at it by introspection. So, so one such problem, which I think is a good candidate, is the word completion problem. So here you're given a sentence. I mean, it's very good to have a sentence which is, say, a headline from a newspaper or a web page, because they're usually concise. And delete a word, and you have to guess the word. Okay, it's a good game because there's a grand truth. Okay, there's a true word which I deleted, and you have to guess what it is. So actually, these were taken from I think the Times of India website about 18 months ago, if you need to know, because everything comes from a time and place. Okay, so the question is, can you figure out the answer, and then we'll try to find out how you got the answer. Is it by some deep learning, machine learning algorithm or something else? Okay, so what's the missing word in the first one? Cooler. Okay, very good, very good. Okay, so this one is something which you'd imagine a machine learning algorithm with lots of text thrown at it could solve, because this pattern of warm but cooler is something which, if you had a billion sentences, you'd find. So what about the second one? 10 Delhi metro stations to go.
Wait.
Sorry? Okay, so so this shows there's a bit of knowledge involved here. So as I said, this was in India about 18 months ago. So anyway, the answer is cashless. Okay, so cash was an important topic in India at that time because it vanished. So if you knew that piece of information, you may have learned this sentence. So this is an example of a sentence which is unlikely that a machine learning algorithm thrown at lots of a billion sentences could figure out, because there aren't too many sentences like this. And also it's based on the knowledge you needed is based on some recent news, some facts, which aren't typical of your big database of things. So usually it's recent events, one reason why you need to use some reasoning, and some facts which may not have been available in a big database of examples means that you have to go beyond just machine learning. Okay, what about the third one? Anyone guess this? Okay. Anyway, answer is jail, actually. But okay, so okay, so maybe some knowledge would be useful for that. So doing some reasoning. Okay, good. Okay, so this task has some commonality with the Turing test. So the two good things are that the performance, there's something which is measured. I can measure how often you're right. There's something quantitative. And the second one, which is very important, is that the knowledge is unrestricted. It's not knowledge about a micro world where you program in knowledge. It's really general human knowledge. Okay, so that's, I think, a very important aspect of the Turing test and of this problem. And so as one approaches it now, I suppose two further angles which are thrown at it if one uses machine learning theory. So one is, of course, that your performance does depend on which world you live in. And in learning theory, there's a distribution where you get the examples from. So you come from a world, a time, and a place. And depending on what knowledge you've gained, you may or may not be able to answer these questions. And the other one is that once you get into algorithms, then some things you may want to solve are computationally feasible and some are not. So the solutions we'll find will be strongly influenced by what we think is computationally feasible. So computational feasibility is a strong guide to everything I'm saying. Okay, and so the formulation I'll give, so this is a formulation called robust logic, which I've pursued for quite a long time. So it comes into lots of obstacles of efficient computation. So we have to do reasoning, you have to do learning, and also it's in this multi-object setting, as in traditional AI, where it's not just one object which you're looking at. It is a picture of an elephant, but you entertain the idea that there are 5 people here, and what are the relationships? And each of these 3 things independently give rise to exponential difficulty, so somehow you have to control those. So my angle or my formulation on how you put together this semantics for going beyond machine learning is influenced by what I think is almost forced by computational limitations. Okay, so everything I'm saying comes from a theoretical perspective of what's computationally feasible. Okay, so I'll describe to you this kind of robust logic, which is like a semantics for cognition, which incorporates learning but also reasoning. So that's basically. So the first idea is taken from cognitive science, but it's also forced by computation. Is the idea of a working memory. So the idea that the computation always goes through like a small window, which is between you and the world, and all the information which you process goes through this small window. So it could be, in a computing terms, it could be compared to registers in a computer. So in a computer, most of it just stores things and ships things around. But the small part of it actually processes things anew. For the first time, 2 numbers are multiplied. So the working memory is where, for the first time, you go somewhere and you absorb what's there. Okay, so your enormous amount of memory just sits there passively in your mind. Sometimes you replace it, sometimes you add some new memory, but when you combine information you have for the first time, it is this mind's eye, or working memory. Okay, and the reasons I need it are first that there are fairly complex computations going on there, but the second one, even more importantly, is that the learning I do will be entirely on the basis of what I see in my mind's eye. Okay, so very briefly, my solution to the problem of semantics is that all your semantics is relative to what you see in your mind's eye. Okay, so the only thing real for you is your mind's eye, which somehow there's a real world outside, there's your big brain inside, but what's in your mind's eye is something simple, because that simplicity enables you to make generalizations about it. Okay, so what's this mind's eye? So you wake up in the morning and you have some tokens. So cognitive scientists talk about 7 chunks. So I talk about tokens, and maybe you have 20. I don't know how many tokens you have. But they're featureless. But then you suddenly think of something as seen, and maybe you think of an elephant. Okay, that's an elephant. And then you think that elephant likes something. The second object likes. So you got relationships among your tokens. And then maybe you know some rules. So your big brain has various facts it knows. And one fact may be that elephants like peanuts. Okay? And in this formulation, the idea is that if there's an elephant in your scene, and there's something else which this elephant likes, X2, then you bet it's going to be peanuts. Okay? Maybe it's not true, but that's your belief. Okay, so your mind's eye basically consists of tokens with various predicates attached to them and some new relationships, and these are the examples you experience in life. And everything, all your mind works through these things. This is what you see. You know, what you imagine goes into your mind's eye. What you see from the outside goes into your mind's eye. So this is your big interface, and all your logical rules are going to manipulate these things. Okay, okay, peanuts, right? So now I'm going to describe how, if you want to make a theory of cognition from this, which is computationally limited, what you seem to have to do. Well, many of these things you have to do, others you may have options. But the first thing is that these implications go away, and we need equivalences. Okay, so what we're going to do is that we're going to have a rule, maybe for each word in the dictionary, like peanuts, we're going to have a separate rule, and this rule will be like a learned algorithm. Maybe you've got a deep network in your brain for every word in the dictionary. And basically this deep network or shallow network or perceptron or whatever your learning algorithm is basically a learned criterion of when what you're looking at is peanuts. Okay. So in the machine learning, you try to categorize something, and it's an if and only if condition. It's an approximate one, but it's an if and only if. So if your thing says yes, it should be peanuts. If your circuit says no, it should not be peanuts. So it's an equivalence thing. Okay. But the idea is that we'll have lots of these circuits. Each predicts something different. And so in your mind's eye, you have some things committed like an elephant and like something. And then you search around in your brain for a rule where the output is predicted. Okay. So your peanut predicting circuit would say, yes, this object is peanuts. Okay. So okay, so another one would be, for the rule you may have used for the last puzzle, is that if there's a child and the mother of the child, then often the mother is in the same place as the child. And that's how you reason that the mother would be in jail too. And the point that we have an equivalence there is the price you have to pay for making this a learning system. Okay, so I'll describe some of these features of this what I call robust logic, which define a kind of semantics for cognition. Okay, okay, and these are all driven by computational considerations. As I said, some you have some options on. So, okay, so the second thing is that we have some quantifiers, like they're existent for all. And so one big puzzle, which I think I've always wondered about, is that when you say all men are mortal, so what does it mean? Is it all men on Earth, all men ever, all men on all planets? Has someone checked it out? So it seems very problematic, this statement, okay? So this is much more modest. So here the quantifiers just refer to what's in your mind's eye at the time. Okay, there's no outside world. Okay, so but the quantifiers say that there's one object in your mind's eye, which is a child, another object which specifies a mother. You may also discuss whether every object in your mind's eye is something, but that's all. There's no reference to an outside world. Okay. Okay, so a third feature. So we're going to build some semantics for cognition based on learning. So what about consistency? Formal logic is famous for everything being consistent. What about this logic? Answer is no. Okay, nowhere. Okay, so here your brain is going to have all these learned rules about all kinds of stuff. No one promises consistency. You just go around with inconsistent rules. So sometimes your mind's eye will see two contradictory predictions. You should go left, you should go right. Well, you have to deal with that at the time. But no one goes around guaranteeing that your rules are consistent. In instances where they're inconsistent, you have to deal with it. And maybe you update your rules. Maybe you learn from it. Okay. Okay, so that's the third one. Okay, so the fourth one, so let's go back to learning. So the real semantics is going to be given here by learning, and this will be the semantics of statistical learning or back learning, which I'll just describe in a second. So this is the connection with the outside world. And so the idea is that you have some, okay, so this is still not the, okay. No. Okay, so let's define back learning. So here you've got a hidden function, which for some, so the blue circle are all possible inputs, which may be an incredible number of different ones. And some are positive examples of this concept, like peanuts, some are negative examples. And you're trying to learn this. And so what you learn is a hypothesis H, which will be different from the truth, because in any complicated enough world you will make errors. But this probably approximately correct model of learning describes in a common sense way what are reasonable expectations. And these are that the error be small. So you'll only consider learning to have been successful if the error is small. You want to be general, so the distribution of possible examples can be arbitrary. So the relative frequency of the dots in your blue circle can be arbitrary. But then you only test this for the same distribution. So the magic is that very rare cases you don't have to be able to treat, because you probably won't see them in training, and you won't see them in testing either. Okay, and then the meat of this is that when you learn, you want to be able to reduce the errors to be arbitrarily small, but at some cost, and the cost is more examples and more computation. But although you're paying this cost is still bearable. It only grows polynomially in the various costs. Okay, so the main meat here is that there's a phenomenon in which you can learn, in which you can reduce accuracy arbitrarily at a certain tolerable cost. And in some sense, obviously, recent experience in machine learning is that by investing, say, 1,000 times more computational power, as we do now than we used to, we do get more accurate learning. Okay, so this is a probabilistic definition of when a function is successful. Okay, so we're going to learn these rules in this sense, but the rules will apply to these things in your mind's eye. Okay, so we learn to predict our mind's eye well. Okay, so I look around, I'll make predictions of what I see. Okay, so this is the semantics. Okay, so now we get into more kind of philosophical issues. So what fascinated me about learning initially is this cognitive aspect, that there's this very predictable phenomenon that children see fruits, animals, furniture in their various places, and see examples. They learn to categorize them, and even when they meet students from other places, there's an amazing amount of agreement. Okay, so this generalization works amazingly well, although we've all seen different examples. But so the idea is that we all live in one world. There's a one world we all learn from and are tested from. But then this becomes a bit more challenging if we do more complex things. So answering this question of did Aristotle have a laptop? So so what exactly did we? We can all answer the question, but what exactly do we have in common, which enables us to say that? We haven't seen the same sentences about Aristotle. It's a bit harder to pin down. So there's a philosophical question of how on earth it's even possible. Okay, so here's a slightly technical version of it, but it's not very technical. So the idea is that these examples we see in our mind's eye, they've got some features, and there's some ground truth. But really, this is an exercise in incomplete information. So the amount of information we see in our mind's eye is very limited, and most things are not specified. So, for example, a problem in AI is this thing about Tweety, that if I say Tweety is a bird, you predict it flies. But if I additionally tell you that Tweety is a penguin, then you say it doesn't fly. And in most logics, this is contradictory, because if I give you more information, you shouldn't change your mind. But this shouldn't sink our theory. We should have some reasonable explanation. And the simplest explanation is that the omission of a detail is information itself. Okay, so in fact, you should regard this an example as specifying some yeses and nos, but also saying that certain features are unspecified. Okay, so if I see a bird and no one tells me it's a penguin, that's good information. If it was a penguin, you would have told me. Okay, so if you didn't tell me it's a penguin, it's unreasonable to deduce that it flies. So treating the unknown as a honest value is a reasonable thing to do, and it kind of works. Okay, so that's what we do. So non-monotonicity is this feature that is this problem with this example. Otherwise, that when you find out more, you change your mind. So in this formulation, that just you define that away. Okay, and then so what we do is, in fact, we have to introduce a second notion of unknown. So so what's prediction? So if I tell you this grand truth, what do I predict? So the formulation here is that my prediction is exactly the same way as in this hidden word problem, that I give you a real example, I hide some feature, and you have to predict what it was. Okay. Okay. Okay, and then, okay, so I think this is the last one. So this inductive learning is kind of wonderful, solved everything, but it does have some limitations. And so one limitation which has been identified is that, so if you're learning concepts on top of each other, and you're learning from someone who doesn't know too well, then it's problematic, okay? So, so if you're trying to learn many functions at the same time, supposing you're trying to learn all the words in the English dictionary at the same time, maybe in terms of each other, and you're uncertain about each one, then it's hard to make learning work. And so what I'm trying to do is a theory of cognition which can do this. Okay, so there's some contradiction. So again, to make it work, what I have to do is I assume that the examples do come with correct labels. So the teaching is done by experts. So for example, when you learn mathematics, you learn groups, rings, fields, or whatever. But the next concept you're told by a reliable teacher who understands the concepts, not by someone who points their fingers at random. So this somehow points to the fact that maybe learning complicated concepts is difficult. You can't just do it by having people sit around and learning from each other. Okay, it's a long process. You have to develop expertise, and then it's only the real expert who should listen to, because learning from unreliable classifications is kind of dangerous, and you won't learn things. Okay, so to learn complicated things, you do have to have correctly labeled concepts rather than concepts you're just in the process of learning. Of course, there's much work on this issue of noise, etc. But to make the system work, we need all these things. Okay. Okay. So what I'm doing is, okay. So this is what I'm trying to do. I'm trying to learn thousands of these rules together about these scenes, so that I can act more intelligently. Okay. So let's see what. Okay. So maybe I'll go back to the theory. Okay. So maybe I'll just describe an experiment. So this was done several years ago with a student, Loidos Michael, so the idea was that we wanted to learn rules, learn facts from the world in such a way that with these facts we could reason better than without them. Okay, so there's always a base pure learning solution where you give lots of examples to your learning algorithm and make a prediction. Question is, can you do better by doing some reasoning? Okay, so that's the basic question. And what we were doing was this problem of missing word. And the Wall Street Journal had there was a good database of sentences from the Wall Street Journal, so that's what we used. And so we did some very simple natural language processing. Okay, so we also used some reliable knowledge, like a dictionary. So if two words mean the same thing, we use that kind of information. Okay, So this, we try to learn facts from the Wall Street Journal, and this is very simple natural language processing. We all learn facts from single sentences. So it was rather restricted. Okay, and so the question was whether using reasoning from these learned rules, you could do better than some baseline method which just applies black box machine learning to sentences. Okay, so black box machine learning just means that I give you lots of sentences, I remove a word and train you to predict what the missing word is. And when I add rules, I use other facts about the world. Okay, and so, so maybe it's better if I give the theory a bit before I describe the experiment. Okay, so the theory is, I have 3 slides about this. It's very close to what I've already described. So it says that you got your mind's eye, you got T objects in your mind's eye you wake up with. So you're trying to learn a rule with the right-hand side. So right-hand side could just be a relation which says peanuts, so X3 is peanuts, or it could be a relation, like something is the mother of something else. And the left-hand side is the rule you're learning. And so you could use any complicated, any learning algorithm you like, deep learning or whatever your favorite one is. So we use a simple linear learner. So the features could be compound features, so with quantifiers. So you could express the fact that x1 is the mother of x2, or x3 is above x4, and you could quantify in what's in the picture. And then you learn these rules, and basically your learning box gave whatever the properties of the learning box were inherited by this learning method. And if you wanted your learning to be reliable or efficient in other senses, you just use your favorite learning method. Okay, so we just learned rules like these. Okay, we just learned rules like these. So the learning works. Okay, so let's stop there. And then there's some results which justify the whole formulation, which is that you can do various things efficiently. And the main point is that when you learn these rules, what you want to do is to chain rules together to draw conclusions. Okay, so if you want to draw a conclusion that Aristotle didn't have a laptop, you'd probably have to chain together some rules you've learned and how to do that. So while learning is such an error-prone process, when you learn several rules and chain them together, that's even more dangerous, more errors. But you've got some theorems which have some guarantees. So it says that if the rules you've learned are independently quite accurate, then your conclusion will be quite accurate. So this mimics the theorems in logic that you can chain together valid rules. Okay, so everything is polynomial time. The only one constraint is that for my relations, the arities have to be constant. The complexity grows exponentially with arity. So if I have a relation on 2 things, like 2 people next to each other, or 3 people are having lunch, that's okay. But I don't want a relation on 100 people. Okay. So we'll break up. So presumably in cognition we do break up large crowds into smaller units. Okay. So I may say there are 2 groups of people here. Those in the front row and the rest. Okay. It makes it simple for me. Two objects. Okay. And okay. So in this formulation I've described, what you can show is that both reasoning and learning are efficient, and the reasoning delivers what you want, which is that your conclusions will be accurate in this probabilistic sense. Okay. Okay, so then we did this experiment where we tried to ask whether in practice you could actually learn good rules. Okay. And so as I said, the learning method we used were linear inequalities. There weren't deep networks, so it was linear inequalities. And so a typical rule was that supposing, okay, there's a missing word is the missing word price. Okay, so for each possible word which we're entertaining, we're learning a separate rule. So this rule said that, so the first thing said that if there's a word, which is the word bargain, and the sentence said that this bargain lowers y, then let's guess that y is price. A bargain usually lowers price. Okay, so that's a reasonable evidence for price being lowered. And the second says that if competition lowers something, competition also lowers price. So what we learned is some very complicated rule which somehow assembles lots of evidence as to whether the missing word is price or not. And this we learned entirely from just text. Okay. Okay. So it's a very noisy domain. Many of the rules you couldn't make too much sense of, and they didn't work too well. But we chose 268 words, which occurred frequently enough that we had some chance of predicting this. And basically the result was that we could do something useful. So the trade-off is that standard machine learning is very powerful. So just the statistical weight of the words adjacent to a missing word give you so much evidence of what the missing word is that even that it's hard to compete with. It's hard to compete with the brute statistics. But somehow, if we want to be a bit more intelligent, we have to. If we want to reason and understand what's going on, we have to, and that's what we try to do. So we try to see whether these noisy rules could somehow compete with, these noisy rules plus the weight of statistics could compete with just the weight of statistics. And okay, so we had various results. So the only thing to look at is that, okay, so the top, so we listed these 268 words from left to right, depending on how well our method worked. The rightmost words were the easiest for our method to work on, and the difference was the red and the blue lines, the E and the D, and that's basically the difference between how well we could predict with rules as compared to without rules. So for about half the words, we could produce no improvement, and then for some words, we could produce significant improvement. So maybe we could learn a lot of information about price from the Wall Street Journal, which somehow, so we could make predictions about when the missing word was price, which wasn't obvious just from the neighboring words in the text. Okay, so this is weak evidence that this thing kind of does something. Okay, so obviously the goal is if you want to demonstrate that this is a good approach to cognition, one would want to demonstrate this on a bigger scale. But the difficulty is finding good teaching materials. Okay, so here we use the Wall Street Journal, and we found that maybe the Wall Street Journal doesn't have that much useful information for us to learn. Okay, so as far as we could tell, there's a lot of gossip in the newspaper. You could tell, who was up, who was down, who was out. But you probably wouldn't learn to be a good businessman from reading the newspaper. The information wasn't there. It was assumed you knew it maybe, but you couldn't learn it from there. You probably couldn't learn economics either. So it was pretty, we couldn't find that much information, but maybe with better techniques we could have. So the general question is, how do we get information in a computer for it to learn rules, which is hard to put one's hands on? And well, of course, many people work in this area, and the answer is always the web. Go to the web. So I tried. So I wanted to find out whether the elephants are gray, pink, or white, and I put it in Google, and it was hard to tell. It wasn't decisive what color elephant was. So I thought, well, let's go to a specialist. Let's go to Google Scholar, and this is what I found. Okay, so it's a hard problem. Okay, so it seems that well, in human education, we spend inordinate amount of effort into preparing teaching materials for students at all levels. Okay, so it's a big part of education is preparation of teaching materials, and it seems to me that probably in AI it's going to be the same thing. That the algorithm, there's some good algorithms which we have may already be pretty good, that we need better algorithms, but we only so many better algorithms, but putting new information into a computer, which is hard to get at the moment, is labor intensive, and maybe that's where much effort will go. So for example, if you want to make a computer have common sense in the human sense, so common sense usually means knowledge which humans have great interest in, but they haven't written down anywhere, then you may need a very large project like that. So of putting it in. So where learning comes in, of course, is that what you hope is that learning makes this knowledge base robust. So instead of having lots of programmers programming in this knowledge and possibly being inconsistent, if you just pour it in the machine learning system, that will figure out some consistent view of the knowledge, and it will make generalizations in whatever internal representation it has. So the robustness in the robust logic comes from the fact that by doing learning, you hope to make it robust. Okay, more so than a human could do by programming. Okay, so as a technological problem, we'd want to solve the AI problem of putting into computers knowledge which is hard to put into computers, which is what we call common sense knowledge, and we want to do it robustly by learning. So this kind of approach of putting in information by learning, so one could say there's an existence proof that it has to work, because that's how we got it. So if you further entertain the idea that evolution is also a learning process, then all the knowledge we have of any form we have through some learning process. So all we have to do in AI is to reproduce this learning process. So this thing has to work. Of course, the challenge is that the training set for evolution may have been lost. In fact, it is lost. So the fact that all the information in our biology has been gained by learning may not be so easily exploitable if we've learned the training set. But so we have to compensate somehow. But so the general approach of gathering information by a learning process seems to be hard to argue with. Okay. So that's basically what I have to say. So what I've said is sometimes not very exotic. So in fact, I saw this paper in Science magazine last December, and basically that was a non-technical article trying to explain to general scientific public of the implications to work of machine learning. So it's written by someone from the Sloan School and Tom Mitchell, who's a learning person from CMU. And so they try to specify, if you're worried about losing your job, who should be worried? And so what they said is that the kind of tasks for which machine learning is useful now, this just functionally, independent of any, have 5 positive things in common and 3 negative things which they don't have. So the 5 things in common, if you're worried about your job, are the following: that the function you do has well-defined inputs and outputs. Large data sets can exist or can be created which exemplify your job. It's clear what's good and bad. Performance, tolerance to errors. So if your job is totally intolerant to error, maybe machine learning is the wrong approach. And also the function shouldn't change too much with time, because if it changes with time again, machine learning may not be so good. So these 5 requirements are technically what is supervised learning. And I suppose packed learning is basically corresponds to a definition of these 3 things. And then they mentioned 3 things which the job should not have. And these are the things which I think we should do in the future. And so the first one is no long chains of reasoning that depend on diverse background knowledge or common sense. Okay, so these are things which we cannot do at the moment, but we want to do. And so robust logic is aimed to do exactly this, so that's good. So no need for detailed explanation or decision. So again, machine learning methods, as is, don't give you convincing explanations of what they're doing. So with robust logic, at least, the logical part gives you explanations. So there's a part which you use black box learning methods, but in the end, you learn rules in which you believe. Okay, so these are the rules on which you operate. And so if you make a decision, you can exhibit the rules which you're using. Okay, so it solves those two problems. So the last one is that no specialized dexterity, physical skills, or mobility required. So obviously, I don't address this directly, but again, to do these other things, you'd imagine that you need some rules, some language or rules which are outside the machine learning box, that you have to have some ways, some rules about the physical world and operating on it. So this kind of approach does address something like that. So anyway, so I thought this has got an interesting summary of the functionality level of what machine learning does at the moment and what we hope you could extend it to. Okay, thank you.
So I think we have time for some questions, which I'll help moderate them up here.
Thanks for the nice presentation. You started by talking about Aristotle's inductive reasoning, and which is mostly formulated as a learning in your learning theoretic paradigm. There are some follow-up extensions or formulations of reasoning by Aristotle's students or other logicians or philosophers, such as deductive reasoning or abductive reasoning. How do those reasoning frameworks are supported in your formulation here?
So I'm not quite sure whether there's a one-to-one correspondence between anything I do here and any of those. So certainly the back model aims to capture a very specific meaning of induction, which is this generalization at this propositional level. And then I add something corresponding to what looks like logic on top of this. So I don't know if a one-to-one correspondence. I think there may be issues of the semantics being different.
So you mentioned this kind of bottleneck of having working memory, the mind's eye. Is that needed so that it's computationally efficient to be able to do this chaining or inference? Is that?
Yeah. So most basically, it's needed to make my rules learnable. Okay, so the bottleneck is the number of okay, so the real bottleneck is the arity of the relations, and it's only polynomial in the number of tokens. But yeah, so I'm going to learn from these examples I see in my mind's eye, and I have to keep them simple to keep my learning algorithm workable. Okay, so and it's a simple mind's eye just because learning is difficult.
But then does that mean there's some sort of restriction on what you can actually get from the real world? I mean, if a computer actually had a larger working memory than a human, would you imagine that then the rules that you could learn would be a lot more efficient or more?
Well, no, I think there may be fundamental impossibility of learning from a much bigger mind's eye. So I think the mind's eye may be limited by ultimate computational considerations. Okay, maybe you can do bigger than we do in our brains, but I think there are limitations. Yeah.
Yes. Following up on the mind's eye idea, so let's suppose you carry on with this and you solve the problem, say, to your satisfaction within that domain. There remains another issue, which is how does the perceptual system, say, get information? Do you think that, and I guess my question is, and many people work on that question, but principles you get
Yes, yeah.
from solving this version of the problem would be helpful in solving that problem, which also has been approached with machine learning.
Right. So I'm trying to do a formulation to keep things computationally feasible. And so those questions I'd formulate this question of, how you need some other ways of operating your mind's eye, like how you direct it to how you control what goes into it. So you're talking about things like attention and...
Well, actually, just object recognition. Like if you're going to postulate that the mind's eye knows there's an elephant in the sea.
Yes,
Something had to have gotten it there, and that's a hard problem which machine learning has been applied to.
Yes.
I'm just wondering whether, if you thought you solved the reasoning, I'll call it the reasoning or the generalization problem in the domain you're working on, whether those principles would map onto the, I'll call it the problem of perception or object recognition, or whether that problem has such a different structure that it would proceed in its own way.
Yeah. I think they're different problems, but I think if you solve your problem, you still need to solve my problem, I think, too. Okay, so I think we need to solve both problems, and they're not the same now. Yes. Okay, yeah.
Slightly related to that, do you think the robust logic framework could be used to do causal inference? And if yes, do you think that could lead to a new paradigm of algorithms that interact with the world as we see in control theory or reinforcement learning?
To do causal inference, you mean to figure out in the world what causes what?
Yeah, if I do X, will Y happens?
Yeah. Well, I presume this is exactly what we do, right, with our mind's eye, right? So this is what humans do. So presumably, we learn rules which are effective rules for making deductions about cause. So sure. So any kind of inference which we do, I hope we can also do in this mind's eye. Yes. Okay.
So you said that the results that you get with robust algorithm on your experiments were quite noisy and less interpretable that we might want to. What do you think would be needed to alleviate the problem, and in general, what are the challenges for the framework to become more of a real world framework that is applicable to many problems?
Yeah, well, I think the main thing is what I mentioned is certainly having big enough databases. So even 500,000 words doesn't have too many occurrences of any one word, interesting word. So one needs bigger databases, possibly curated in some interesting way. But even the experiment we did was pretty basic. So our natural language processing was extremely basic. We looked at single sentences. One could do much better with more sophisticated natural language processing. So if one was looking at natural language, one could do much better than we did with bigger databases and better NLP, I think, and more computation power.
In your experiment, if you look at the wrong answers that your method got and the same method, is there I know you want to be quantitative, but is there a qualitative difference in the answer? So that, for instance, where, you might imagine the wrong answer, the right answer is price, but the answer that's given is value. Well, that's that's the right ballpark, right? But Marmaduke, or I don't know, that's not even that's a person, but elephant, or
Yeah.
So, did you do any work of that sort of comparing?
Yeah, so I don't know. I mean, I'm sure our experiment was too simple, so I'm sure it had some absurdities. So I'm sure I can't be. There's no reason I'm sure I wouldn't be proud of how it did on. It probably made some very bad mistakes, I guess. I don't know, but I guess.
I'm not.
Yeah.
But a pure machine learning
Yes.
method might also make.
Sure. Yeah. So I just don't know. I don't think we did a big enough experiment to give a good answer to that. But certainly a great question. Yeah.
If I heard part of what you said, you mentioned that there were quite a lot of rules that you generated in your experiment, and some of them maybe weren't so straightforward for a human to interpret, and so you looked at certain words, predicting certain words. Did you attempt at all, or do you think it just wouldn't be feasible to build into the thing some way of either restricting which rules you're applying to certain cases, or kind of using context to rely more heavily on some rules rather than others?
Well, I think the main thing we found is that we only used rules which were extremely good, which were, where the statistical evidence was overwhelming that it was good. Okay, so using rules which had some uncertainty was very bad. Okay, so using rules which we had a very high confidence on because they predicted the training set perfectly. That's the one thing we found which was useful. In a bigger experiment, I think there's a lot of scope for what you're saying, I think, but we didn't explore that.
Why don't we take one more, and then there's a reception afterwards, although the ratio of questions to answers is pretty high. But let's take one more question and then break.
So I think at least the examples that you showed earlier, the implicit ontology underlying the rules is that there are objects and relationships between objects. Do you think it would be rewarding to look at more complex or even like dynamic ontologies? And if so, is there any work being done on expanding robust logic to like these more complex ontologies?
No, I didn't have anything specific. So by dynamic, you mean, so what do you have in mind?
For example, like objects have properties, some objects are instances of other objects. It seemed like all the rules that were learned were just between is this an object and what are the relationships between kinds of objects?
Yeah, well, I think many of these things one could do, I think, this way. So I don't think this method is restricted. As long as you can propositionalize it, as long as you can make a propositional thing out of the predicate case, without things blowing up too much, you can do it, I think.